Welcome viewers to the second lecture for the online series of lectures for the course of Algebraic Topology 1. This lecture is going to be dedicated to the notion of fundamental group. We will first define the fundamental group of a topological space relative to a base point, and then we'll discuss various properties of fundamental group. The basic goal for this lecture would be to show that the concept of fundamental group is a topological invariant. So let's get started with the concept of the fundamental group. Okay. Alright, so given a topological space X, we have seen that if we take all the path homotopy classes of paths, all path homotopy classes of paths, okay, it is basically a set of equivalence classes, right? Where each class represents a path homotopy class. Right. So we have seen that in this set, there is not always this product defined. Okay. So if I choose any class from this set, I cannot always define the product. Okay, or the concatenation of paths is not always defined in this set. It requires the path F to have the final point to be the same as the initial point of the path G. Okay, and if it is not satisfied, then we cannot take the product of two paths in this class. But this problem can be fixed by in the following way. If I pick out a distinguished point x0 in X, okay, and I only consider the path homotopy classes of loops. By loop I mean a path that begins and ends at the same point. Okay, so if I take all path homotopy classes of loops starting and ending at the same point x0, something like this. If this is this topological space X, this is the fixed point that we have chosen, x0, and if we consider paths like this that begins and ends at the point x0, we say that this loop is based at x0. So if we choose the path homotopy classes of all such loops, then we immediately see that the product star is well defined in this set, right? So any class can be we can take the product of any class with any other class in this set, right? The set of path homotopy classes of loops based at x0. Okay, so that resolves the problem. So this set of the path homotopy classes of loops based at a distinguished point x0 in X will be called the fundamental group of X relative to this base point x0. Now let me give you the definition, the formal definition of the fundamental group of a topological space relative to a base point. Definition: let X be a space and pick out this point x0 in this topological space X. Now let me define a loop first. I've already defined it informally. A path in X that begins and ends at x0 is called a loop based at x0. Okay, this is called a loop based at that fixed point x0, that base point x0. Okay, the set of all path homotopy classes of loops based at x0 equipped with the operation star that we call concatenation of paths between any two path homotopy classes is called the fundamental group of X. X relative to the base point x0. It's called the fundamental group of X relative to the base point x0. Okay, so this is the definition and the notation. It is denoted by, this fundamental group is denoted by pi 1 of x comma x0. Okay, now I want you to convince yourself that this set has the structure of a group. So look at the statement of theorem 1 and convince yourself that this set is indeed a group. Okay, convince yourself that pi x comma x0 is indeed a group by consulting theorem 1 from lecture 1. Okay, now I give you the first example of this lecture. Example 1. So let us take the Euclidean space R to the n and consider the fundamental group of R to the n with respect to with respect to certain point x0, and we see that this group is the trivial group. Okay, so the notion of trivial group means that there is only one element in the group which is the identity of the group. Okay, So it trivially satisfies all the axioms, all the properties of a group. Okay, and so this consists of the identity element of the group, which is the constant loop based at x0. Okay, so it's the constant loop that begins and ends at 0, and it means that since it's a loop, it is a map from I to that singleton, right? And of course, e sub x0 is at 0 is the same as e sub x0 at 1 is equal to x0. In fact, for all points of I, e sub x0 at that point is equal to x0. It's a constant loop. Okay, or the constant path in x beginning and ending at x0. So in this example, pi1 r to the n comma x0 is precisely the trivial group. In fact, one can prove that one can prove that if x is a convex subset of r to the n, then pi1 of big X comma x0 is equal to this trivial group, where x0 is a certain point in big X, the convex in the convex subset of R to the n. By convex subset, we mean that if we take any 2 points in the given subset, then the line joining those 2 points lie entirely in that subset. Okay, so intuitively it means that if your subset is something like this, it is not going to be a convex subset, because if you choose these 2 points of this subset, then the joining line between these 2 points is not entirely contained in the subset, so it's not convex. But anything like, a ball, something like a ball is a convex subset, because if you choose any 2 points, say the extreme points, if you pick up, then the line joining them is entirely contained in this set. Okay, all right. So let us see how we can prove this. Okay, so let me erase everything here. Let big X be a convex subset. Let me directly write it as a subspace. Okay, we first take the subset, the convex subset of R to the n, and then equip it with the subspace topology to get a convex subspace of R to the n. Define the continuous map H from I cross I to x in the following way. hs comma t is equal to 1 minus t times f of s plus t times x0, okay, where it is the distinguished point of x, like we have demanded earlier, right? X0 is the distinguished point, where in this case here I have not defined f from I to x is a loop based at x0, okay, and from the definition of a loop based at a certain point, we know that f of 0 is equal to f of 1 is equal to x0 is the point in x. Okay, so now it can be done since this subset of R to the n is a convex subset. So let me write it here. It can be done since x being a subset of R to the n is convex, which means that the straight line given by the above equation, it's a straight line between these 2 points. F of s is a point in x, big X, okay, from the definition of f, right? Since f is a map from I to x, so fs will be in x. So fs is a point in x, and x0 is the distinguished point in x. So this gives a straight line between these 2 points of x. And the entire line joining these 2 points entirely lies inside x by the convexity of x. Okay, so we are good. So this HST can be recast into the following form: is equal to 1 minus t times f of s plus t times e sub x0 of s, right? Because that's the way you define the constant map or constant path, or to be more precise, constant loop at x0. E sub x0 is mapping all of I to that singleton x0, where E sub x0 at s is equal to x0 for all s in I. Okay, now here we immediately see that hs comma 0 is f of s from this equation, and hs comma 1 is e sub x0 of s. h0 comma t is equal to x0 is equal to h1 comma t. You immediately see that, right? So just plug in s to be 0 here and use these facts to find that h0 comma t is x0. Similarly, h1 comma t is x0. This is our equation number 1. Therefore, h from I cross I to x is a continuous map satisfying this equation 1. In other words, H is a path homotopy between the loop F based at x0 and the constant loop at x0. This guy H is a path homotopy between the loop between the loop f based at x0 and the constant loop at x0. Okay. Hence, we see that any loop based at x0, which is the distinguished point of the topological space, with x being so let me write it here. So we see that any loop based at x0 in x with x being convex is path homotopic to the constant loop at the constant loop E sub x0, okay, which means that there is only one class, the class of this constant loop, okay. Therefore, pi 1 x comma x0 is the trivial group, right? The class of E sub x0. Okay, so this is what we wanted to see. Now the question is to what extent the fundamental group depends on the base point. We want to address this question. To what extent the fundamental group depends on the base point. Let's see. So we have a definition now. Let alpha be a path in X, in the topological space X, from the point x0 to x1, okay, which means that alpha is a map from I to this topological space X such that alpha of 0 is equal to x0 and alpha of 1 is equal to x1, okay. One defines alpha hat a map. One defines the map alpha hat from the group, the fundamental group of big X, the topological space X, based at x0 to the fundamental group of big X with reference to the base point x1 by alpha hat of the class of f to be equal to the class of the reverse of alpha star the class of f star the class of alpha. Okay, alright, so this is how you define this map alpha hat. So where you know this class of f belongs to this set, which is the fundamental group of x with with reference to this base point x0. Okay, this is how you define this. Okay, so this is how you define this map alpha hat. Okay, and okay, let's quickly check that this guy is indeed in this set, because alpha hat, so this is the point x0, this is the point x1, so it's alpha bar. Alpha bar is the reverse of alpha. Alpha is from x0 to x1, and alpha bar is the reverse of alpha, which is the path from x1 to x0. So alpha bar is the path from x1 to x0, and then f is a loop from based at x0, meaning that it's a path from x0 to itself, and then alpha is a path from x0 to x1, which means that the reverse of alpha star f star alpha is a loop based at x1. In other words, it's a path from x1 to itself. Okay, so we get an element here, and given the element f here. Okay, so let me draw the picture. So this is our topological space X. This is the point x0. This is the point x1. So I go from x0 to x1 via alpha, and the reverse of alpha take me from x1 to x0, and at x0 is the loop based, which is f, right? So from this picture you see that this path is a path from x1 to itself, right? Via alpha bar you go from x1 to x0, and then via loop f you come back to x0 from x0, and then via alpha you go to x1 from x0. So together the product gives us a loop from x based at x1. Okay, now why is this alpha hat well defined? Since the operation star is well defined, is a well defined product in the path homotopy classes. Okay, that is the reason this alpha hat is well defined. Okay, so now so this alpha hat we defined as a map from the fundamental group of x with reference to the base point x0 to the fundamental group of X with reference to the base point x1 by alpha hat F is equal to alpha bar star F star alpha. Okay, and this is well defined. Okay, now the theorem 2 states that the map alpha hat is a group isomorphism. Okay, for the group isomorphism we need to first prove that it's a group homomorphism, and then we prove that it's a bijective map. Alright, that way we prove that the corresponding map is a group isomorphism. So let's first try to prove that it's a group homomorphism. Okay, which means that the group structure is preserved under this map. Okay, so let's take alpha. So this is what we want to prove. We want to prove that alpha hat of F star alpha hat of G is equal to alpha hat of F star G. Then we are done proving that it's a group homomorphism. So let's start with the left hand side, which is alpha hat of F star alpha hat of G. Okay, by definition of alpha hat, it is going to be alpha bar, which is the reverse of alpha, star F star alpha. So star for alpha hat of G, we have again alpha bar, and then we have G, and then we have alpha, right? Then by invoking associativity, we can take the product here first to have alpha bar here, star F star, what is alpha? Alpha times alpha star, alpha times alpha bar is, so alpha is the path from x0 to x1, so it's the loop based at x0, right? It's the constant loop. From the definition, it's going to be the identity. So alpha bar is the inverse of alpha, so it's going to be the identity loop, right? And since f is a loop based at x0, so I can take the product of f with the identity element of the group to get this element back, the loop itself, right? So which means that this is nothing but alpha hat of F star G, right? This is the right hand side. So now with unproving that alpha hat is a group homomorphism. So to prove that alpha hat is a bijective map, we try to find the inverse of alpha hat. That will prove that it's indeed bijective. Okay. In other words, we want to show that alpha hat is invertible. Now let us show that alpha hat is invertible. We do this by showing that by showing that if beta is equal to alpha bar denotes the reverse of alpha, then beta hat represents or denotes the inverse of alpha hat. That's the claim. Okay. So if beta is equal to alpha bar, it is immediate that beta bar or the reverse of beta is the path alpha itself, right? The reverse of the reverse gives the original path. Okay, so let H be an element of the fundamental group of X based at, with reference to this base point x1, that is H is the loop based at x1, then beta hat H, okay, beta hat of H is equal to beta bar star H star beta. It's the reverse of beta. Which is the same as alpha star H star alpha bar. Okay, E is immediate that it's a loop. This thing is a loop based at x0, right? Because alpha is a path from x0 to x1, and then H is a loop based at x1, and then alpha bar is a path from x1 to x0. So the whole thing is a path based at x0. Therefore, alpha hat of beta hat of H is going to be, using the definition of alpha hat, is going to be alpha bar star, and beta hat at H is this guy, right? Alpha star H star alpha bar star and then alpha. Then using associativity of this product, we can write it as alpha bar star alpha star H star alpha bar star alpha, right? And alpha bar star alpha is going to be a loop based at x1, is going to be a loop which is the constant loop at x1. That is the identity element of the group. The identity element of the fundamental group of X with reference to the base point x1. Okay, star H star E sub x1. Okay, and write H star E sub x1 is again H, since this is the group H, so all of them, they are all in the group, in this group, right? So we see that this is H. Similarly, so let me erase this top part. One can go ahead to show the following. Let this loop is in the be in the fundamental group of X with respect to the base point x0, then beta hat of alpha hat of f, right? By the definition of beta is going to be, well, let me write this action of alpha hat on f to be alpha bar star f star alpha, right? And by the definition of beta bar, this is going to be alpha star this whole thing, right? Alpha bar star f star alpha, then star alpha bar. Using associativity, I can separate the products and take those products first. Star f and then star alpha star alpha bar. Okay? And alpha star alpha bar is going to be a loop, the constant loop at x0, which is precisely the identity element of this group. Okay? And you see that, so with respect to the product here in this group, we immediately obtain this. Alright, so we have seen that, so it proves that. So using this and this, we conclude that beta hat is indeed the inverse of alpha hat. Okay, so in particular, this identity means that alpha hat composed with beta hat, the composition of these two maps is so alpha hat is the map alpha hat is a map from pi 1 x x0 to pi 1 x x1. Okay, so alpha hat composed with beta hat, and beta hat is the map from pi 1 x comma x1 to pi 1 x comma x0. Okay, so alpha hat composed with beta hat is has to be a map from pi 1 x comma x1 to pi 1 x comma x1, and we have shown that this is the identity map on this pi 1 x comma x1, right? Similarly, we have shown here that beta hat composed with alpha hat is the identity map on pi 1 x comma x0, which means that one is the inverse of the other, or beta hat is indeed the inverse of alpha hat. Okay, so this way we prove that alpha hat is indeed an isomorphism of groups. Okay, so this was theorem 2. Now the corollary to theorem 2, let me state it. It's kind of obvious. Corollary to theorem 2. If big X is path connected and x0 and x1 are 2 points of X, then pi 1 of x comma x0, meaning that the fundamental group of X relative to the base point x0 is isomorphic to the fundamental group of X relative to the base point x1. Okay, all right, so okay, now let X be a topological space that is not path connected. And small x0 is an element of the topological space X. Also, let C be a path component of big X that contains the point x0. So if you are not familiar with these notions of path connectedness and path components of a topological space, then this review is for you. Okay, so let me do a quick review of this connectedness notions. A topological space is path connected. This is the definition of path connectedness. Is path connected if for any, it is important that for any, if you choose any pair of points from this topological space given by x0 and x1, there is a path from x0 to x1. Okay, then you say that the topological space is path connected. So an important fact to follow: if the topological space is path connected, then it's automatically connected. Then X is connected. Okay, but the converse is not true in general, meaning that a connected space may fail to be path connected. So here is a counterexample, which is given by topologist's sine curve. Topologist sine curve. Okay, topologist sine curve. So I'll just give you the example and not prove it. So I just mentioned that it's the counterexample showing that a topological space which is connected but may fail to be path connected. Okay, so here A denotes the set of all ordered pairs in R2 such that the first coordinate is positive and the second coordinate is given by the function y is equal to sine 1 over x. Okay, that is a subset of R2. So intuitively speaking, this gives you a graph like this. As you go closer and closer to 0, it rapidly oscillates. Okay, something like this, and so the points on these curves constitute the set A. Okay, and the closure of this set is this set A union this line segment from -1 to +1. Okay, this is -1, this is +1. So as you go closer and closer to 0, this function oscillates rapidly between -1 and +1 without touching it. Okay, so as you go, so it never touches it. As you go close and close, you get closer and closer to 0. It starts fluctuating rapidly. Okay, so the union, this line segment, which is the point 0 times the interval -1 to 1. Okay, so this guy, so this curve union this line segment is connected but this closure of A is not path connected. I'm not going to prove it, Okay, alright. So now the notion of path component. So we have seen that a connected space may fail to be path connected. Now consider, so given a topological space X, consider the relation twiddle on X by X is declared to be equivalent to Y if there exists a path from X to Y. Okay. One can prove that twiddle is an equivalence relation in fact you should be able to prove it. It's left as an exercise. Okay. And the underlying equivalence classes are called path components of X. Okay, so you are given the topological space X and declare a relation on this topological space X by saying that X is equivalent to Y if there is a path from X to Y in X. Okay, and now the equivalence classes under this equivalence relation, you can, okay, first of all you can show that it's an equivalence relation. So under this equivalence relation, the equivalence classes that partition the entire topological space are called path components of the topological space X. Okay. The equivalence classes are called path components of the topological space X. So if X is path connected, there is only one path component. So if X is path connected, there is only one equivalence class. Okay. All right. Now, okay, so that's all from the review of connectedness. Now we get back to where we were. All the path homotopy classes of loops. Okay, so now get back to where we were, right? So we were given the topological space X that is not path connected, and we chose this point x0 in X, and since it's not path connected, there are more than one path components. We have chosen the path component, we have denoted the path component of X containing the point x0 to be C. Let us denote by C the path component of X that contains the point x0, contains the point x0. Okay, So all the path homotopy classes of loops, it's important to know that all the path homotopy classes of loops based at x0, okay, belong to the same equivalence class, or path component, which we already defined as the path component containing x0, component of x containing x0, okay. And we have denoted this path component by C. So it reduces that the fundamental group of big X relative to the base point x0 is same as the fundamental group of the subspace C, which is the path component of big X containing x0 with respect to the same base point x0. Okay. Good. Now a few facts which we mentioned now. So we have shown earlier that pi 1 big X comma X is isomorphic, right? Is isomorphic to pi 1 X x0 if big X is path connected and these points are any two given points in the topological space big X. Okay, so for any path connected topological space, all such groups are isomorphic to each other. So if we change the base point to any other base point in a path connected topological space, we end up with an isomorphic fundamental group. Okay, so that's what it says. But various paths, okay, so for example, if we choose this fundamental group, and if we choose this fundamental group, okay, where x0 and x1 are 2 points in a path connected topological space, we know that they are isomorphic. But this isomorphism depends on the path chosen from x0 to x1. Okay, we have seen that if you take this path to be alpha, then that isomorphism is denoted by alpha hat that we have seen earlier. This isomorphism is denoted by alpha hat. So the isomorphism turns out to be path dependent, and it can be shown that this isomorphism is independent of the path chosen from x0 to x1 if and only if the underlying fundamental group is abelian. This is something that you are going to prove in one of the exercises, exercise 3, okay, from the homework problems. All right, so this is not the case always. Okay, it is only that it will be the case only when your fundamental group is abelian. Okay, otherwise the path will, the isomorphism will be path dependent. All right. Okay, so these are the two facts that I wanted to emphasize. Now, a very important definition. So I will end this first segment following the definition. So let me give you this definition, a very important definition called simply connected space. It is also important in physics. A simply connected space. Okay, so a space, a topological space X is said to be simply connected if it is a path connected space meaning that there is only one path component, right? It's a path connected space. So in order to be simply connected, it has to be first of all path connected, right? And if the fundamental group of X, big X, relative to a base point x0 is the trivial group. That is pi 1 of X relative to the base point x0 is the constant loop based at x0. Sorry, I need the set to be consisting of this class only, E sub x0. For some and hence any x0 in X. Okay. So if you choose any other point x1 other than x0, so you will get the constant loop based at x1. And that fundamental group also consists of only one point, that is the identity element of the underlying group. Okay, so if it's a simply connected space, then for any point the underlying fundamental group will be trivial. That's what it says. So the easiest example is that of the Euclidean space that we have studied earlier. We have seen that for that space, the fundamental group with respect to any point x0 in Rn is the trivial group, which is the identity element of the group only, consisting of the group consisting of the identity element of the group only. And we have also seen that to generalize it, we could have taken any convex subset X of the Euclidean space R to the n, and ended up with the fundamental group to be the trivial group, ended up with the fundamental group with being the trivial group, right? So any convex subset of the Euclidean space equipped with the subspace topology is also a simply connected space. Okay. Okay, so we often express the fact that pi 1 x comma x0 is the trivial group by writing pi 1 of x comma x0 to be simply 0. Okay, so a simply connected space is a path connected space whose fundamental group with reference to any base point is the trivial group. Okay, so we end the first segment here. In the second segment, we'll come back with stating a lemma and proving it. Okay, thank you for attending the first segment.